Okay, we're gonna do springs today. So we're moving on from welds and those sort of join bolts, welds, all that kind of stuff, and now springs. There's a lot of different types of springs. Today we're gonna focus mainly on these type of springs, coil springs, and compression. So you know push on them. There the chapter. This is chapter 10 in Shigley. Shigley. There are torsion springs, flat springs, all kinds of different springs. We're going to start with compression coil springs, and then I think next we'll do extension, so you stretch them, coil springs, and then torsion springs, and that's probably all we'll do in springs. But there are many types of springs. This is the kind we're looking at today. This one little guy's, just the regular thing out of a pen, a click pen. These actually, I think this one came from the bed on a 3D printer. I'm not sure where that one came from. These are all roughly the same. What you're looking for on the obviously the different sizes, but roughly the same end condition. So you're looking at the ends of these springs, how that's formed. I didn't have an example of some of the different types. These basically all have the same end condition on them. You can kind of see that it's the last few coils here are not the same spacing as the others, so these have been closed. In fact, let's look at a picture of the variety of end conditions. So they're not this plain end where it just kind of chops it off and it's still sticking out, kind of sideways like that. These that we have over here, there's a spot. These are more this squared or closed end, so meaning they took that last round of coil and pinched it in to where it sort of sits flat. It doesn't have the part sticking out here that would make contact on just one little point. They've kind of bent it in. So these are pretty common springs. They're not super special, and they're not just they chopped off the wire and left it as it was. These over here are a little bit different. So this one is not too common. It basically takes the plain end and grinds it flat. So you can kind of see there's this shaded area right here is the part that has been ground flat. So it helps it sit flatter. This one is this version, so they squared off the end, they twisted around flat, and then they ground it. So you can see almost all of the spring will sit flat on a surface. This would be like a valve spring in your car engine would have this sort of spring in there. I didn't want to go take one out to show you, but that's what it would look like, is something like this. These that we have to look at here are this kind of style. Now, the ones here have a variety of different amounts of coils at the end. So this one's got basically one coil at the end. The little one in the spring has maybe 2 or 3 coils here that have been squeezed flat. This one's got maybe half a coil or so. There's a chart in your book. This chart, table 10.1, I guess it's a table, that talks about the different end conditions over here. Well, actually, the end conditions are across the top. And then different variables you might want to find over here they call them terms. So end coils, total coils. These are generic numbers, and as you can see, individual springs can have different numbers of coils on the end and a variety of different things. So the stuff in your chart is kind of generic. If you have a very specific case, you might have to modify this chart a little bit. Now, for what we're going to do, we're going to take the chart as it is, but there are, for instance, these would be the squared or closed, and it says the total coils is equal to the NA. So NA is the number of active coils. So as you can see on our little, this one would probably be the easiest one to see, that is that I've got all these coils in here, and these on the end, they're not really doing anything spring related. They're not storing any energy really or anything. So these are called dead coils, and all of these that actually can compress and extend if you wanted them to, those would be the active coils. And so that's what this chart is telling us, is how to calculate the number of active coils given some other variable. So in this case, the total number of coils, or calculate the total number of coils given the number of active coils. But they're assuming that for the squared end springs, that there are two dead springs, basically coils, two dead coils. But some springs are going to have more than that, some will have less than that. You can have fractions of coils that are dead and active. We're just going to use what the book has as the general guidelines, though. But be aware that these are just general guidelines, and your actual spring you're dealing with might have some different number of active and dead coils on it. So what I thought we would do is take something like this. This is the front suspension from, I think this goes in a truck, so it's a replacement suspension for a mid-70s Chevy truck. But there's a coil spring in the middle of it, and that's what does some of the suspension activities of this piece of equipment. So if you don't recognize what this is, it doesn't matter. But your front wheel, would kind of sit right over on the left-hand side of this thing. So maybe over here you would have your wheel would be mounted to a spindle right here. That's not shown, but we're interested in the coil. So what we need to do is we need some information about this thing. So I went and actually went to this website, whoever selling this product, I don't know, and found what they had. So they had some information about the coil diameter. So that would be, how big of a circle does this coil make? There's actually 3 coil diameters that we need to talk about. They had a little bit of information. I think they had some, or I found some somewhere, about the wire diameter. So this starts out as a piece of wire, and then it gets coiled up to create the coil. And they had some of that information and the material it was made from. So the material was steel, 5160 alloy. Went and found typical properties for that material. So around 30 million psi for the modulus of elasticity, and somewhere around 12 million psi for the modulus of rigidity. A lot of the stress in the coil is held in torsion, so we're going to need modulus of rigidity to deal with that. And we need some modulus of elasticity also. This value here, L0, that's the free length. So that's if this coil was not installed, it's going to be longer by some amount. So when it's just sitting out in the open, that's the free length of the thing. So for this one, it was 12 3/4 inches tall if you just left it sitting on the ground somewhere. It didn't actually say the number of total coils, so I just kind of counted 1, 2, 3, 4, 5, 6. Looks like there's one at the bottom and one at the top, so 8. The way these coils are mounted in here, they just sit in these pockets, and they also have closed ends usually. You can't really see the end of here, but a lot like our springs, probably a lot like maybe this one. They probably look a lot like this one in here, where there's just maybe not even a whole coil on the end that's been coiled over or closed over. So they probably look a lot like this one. They don't look like this, and they usually aren't quite as closed as this one. This is a very thin wire. This one would be a mini version with a couple more coils on it of what we're looking at on our suspension components here. What else did we find? So ID, D, all these variables. We need to talk about what these are. So let's go over here. Let's say that we have our coil, and it's going to be hard to draw a coil. So what I'm going to do is I'm going to draw. Actually, let's zoom out a little bit so I can do this. All right, I'm going to draw coil wire here, one here. And so this would be kind of like a cross section. So this would be the wire. Obviously they'd be connected together somehow, but I'm looking at the cross sections here to be able to label some things. So it just keeps going. I think we said we had eight total coils, so it'd be 8 of these things. I'm not going to draw all of them. You get the idea, I think. We just need to be able to label some things. All right, so there's our kind of sketchy coil. So the different variables that we're looking at, ID is going to be, this is should be a familiar term, maybe it's not, but ID is inner diameter. That's what it typically always means. No matter if you're talking about just a tube of some kind or whatever. But that's going to be if you were to take and measure from the inner edges right here. And then you have a similar one that's OD. Hopefully you can figure out that would be the outer diameter. And you could also assume correctly that you measure to the very outer edges. Neither of these are the variables that we're going to use in our equations, though. The variable we're going to use most is lowercase d and uppercase D without the I or the O or whatever. These are two different things. So D is wire diameter. So that's literally, I guess, this dimension right here. What diameter was the wire that the coil is made of? And then D, with no I, O, or any other subscripts or whatever, that's the mean, so average, coil, whoops, I don't know what I was writing there, coil diameter. So that is the center of one coil over here to the center of the other one. That is the variable we're going to use in our equations, called just D, capital D. Lowercase d is the wire diameter. So we need to know those. The free length for this coil would be from the bottom of here to the top of here. That would be the free length. So it's no force applied to it to compress it or anything. So it's just free. That would be the free length. Let's go back to MathCAD. So we put all those in. ID was 4 inches. Now here you can see I actually calculated the mean coil diameter. ID plus 1 wire diameter. So if you look at our picture, ID is to the inside of the coils, and I added 1 wire diameter. So really I added half here and half here to create 1 coil diameter, and added that to the inside diameter, and that gives me the mean coil diameter. So you'll have to figure out, what which one do you actually need or given? Are you given the inner, the outer? Are you given mean coil diameter? What are you given? I don't know. Okay, let's see what else we have. We have, I put a car weight. This is just a kind of typical car weight for a mid-ish size car. And I made it a nice even numbers, because what I'm assuming here is that the car has 4 wheels, each of which carries 1/4 of the weight. So I made it something that would divide by 4 easily. So 3,200 pounds, and then F is going to be the force applied to one of our springs. Now a car does not have independent suspension on all 4 corners normally, but we could still make this assumption that more or less each corner is going to hold up 1/4 of the weight of the car. Not exactly in all cases, but close enough for what we're going to do. So we got 800 pounds acting on our coil here. Now we get into some of our calculations from the book. So C is just an uppercase C, is called the spring index. And this is just a term that's going to show up in a lot of our other equations, and all it is the ratio of your mean coil diameter. So it's the ratio of the mean coil diameter to the wire diameter. And like I said, it does show up in other equations that we're going to need later on. Also, it's a good measure for if your coil is in the right ratio of, you know, how wide it is to the wire it's made of. And there's some guidelines. Page 520 in chapter 10 has several guidelines. One of them says that for a decent ratio spring, your spring index, should range between 4 and 12. Ours is right at 9. So we're right in the middle of a good range for spring index. So that's a kind of a check that tells you you're on the right track. KB, this is capital K B. This is the Bergstrasser effect. So what this is, or coefficient, it ends up being a coefficient later. There's several of these. There's Bergstrasser, Wall. There might be some others. Bergstrasser is one of the easy ones to calculate right here. This is all it is. You take your spring index and some constants, 4, 2, 4, 3, and calculate this Bergstrasser coefficient. What it does is the coils, like I said, they are supporting or carrying this whatever stresses they're going to carry through a direct shear and a torsional shear on these coils. And so that's relatively easy to calculate. Direct shear is the force you're carrying over the area, you know, the cross-sectional area of the coil, of the wire. This one's not so hard to calculate. You have a center line, and there's some moment that this thing, this one area that I've colored in right here, has some distance from the center line, and there's a force applied, and so you can figure out a moment and calculate this. So you can calculate this direct shear. Let me draw it bigger. You can calculate the direct shear and the torsional shear stress pretty easily. The thing that's difficult is that this is occurring, but this is all wound in a helix, and so there's a curvature effect that gets multiplied to increase these stresses, because not only do you have an area here that has a direct shear and a torsional shear, but it's in a helix that is creating additional effects. And that's what Bergstrasser does for us, is it's that multiplier. So it's kind of, I don't want to call it a stress concentration because it's not doing the same thing like a stress riser would do, but it's having the same effect of increasing the amount of stress that the part is experiencing because of a feature, you know, a geometric feature. And in this case, the feature is that it's curved in a helix. And so Wall and Bergstrasser are two of the ways you can account for that curvature. Bergstrasser is much simpler to calculate. They're both listed in your book, I believe. Let's look. This is equation 10.5 for Bergstrasser. I think Wall, WAHL, is going to be right next to that. But let me make sure. Let's see. Yeah, Wall is simple. Also, it has one more term in it. But they say that the Wall factor and the Bergstrasser factor only vary by 1% difference. So why not use the simpler one? So that's what we're doing. All right. So that's what Bergstrasser is doing for us. It is taking into account the curvature of the wire being wound into a helix that is multiplying the amount of stress that's experienced by the wire. Here, this is equation 1017. So this is the shear stress in the coil. So here they've combined the direct shear and the torsional shear. There's Bergstrasser. There's the force that in our case is 800 pounds. It's the force being applied to the spring to compress it. We are talking about compression springs right now. There's the mean coil diameter. There's the wire diameter. And we've got 84 KSI. That might seem like a lot for normal shear. This is a shear, remember. So it might seem like a high amount, but for typical spring materials, they have, obviously, since they're carrying most of their stress in shear, they do have a higher shear strength than your just average steel. So you can range up to maybe 150 KSI or so. Okay, so we've got a stress calculation here. we want to know the number of active coils. So early on, we had counted that there were 8 total coils. So N sub T is total coils. And that the end conditions were the ones that looked like this. We couldn't actually see them in our picture, but we're going to make this assumption that the end conditions were the closed, but not the ground. A lot of times you'll actually see these coil springs in a automobile suspension will have a little cap that sits on the top that kind of flattens everything out, but without actually grinding them. So they're not the closed and ground, they're just closed. And now I think I realize, well, let's check and see what I did. So number of active coils. I may have made a mistake here, but we can fix it. So they are just, actually they're the same. So let me get my cursor up here. There we go. We have squared or closed ends, is what I've been telling us. NA plus 2 is equal to the total number of coils. So we know, or we counted, that our total number of coils, and if we know that the total number equals NA, the active number, plus 2, then we could also know that, well, the active number is the total minus 2. So that's what I've got over here, is that the active is number of total coils, 8, minus 2, so the 2 on the ends that have been folded in are dead coils. And again, you may not have 2 total coils. You might have like 3/4 of a coil on each end that's dead. You know, we're doing the book table for our calculations here, but in reality, you might have some slightly different number of dead coils. So that gives us 6 active coils. Here's where we don't actually have this. We just have squared ends on our coil, is what I've said earlier. Again, from the picture, we can't actually see the ends. They're, you know, up here somewhere and down there. But typically that's what they are. They're just squared. So that's what we're going to go with. In this case, squared are closed, and squared and ground have the same number of active coils. So we would have the same number. Also, back on here, another one of those guidelines that, like the spring index ranging from 4 to 12. There's a similar one for, let's bring it on our screen here. Let's put it down here. The number of active coils on that same page, page 520, the active coils should be between 3 and 15. So less than 3 and you don't have much of a spring. More than 15 and it's going to be a little unwieldy. It'll probably be unstable, might want to buckle, things like that. We have 6 active coils, so we're right in that mid-range too, so we look like we're good on that size. This is something that should be familiar. Now the calculation for it may not look familiar, but the idea of spring constant should look familiar. And it is basically the same thing it would be in any other kind of spring constant, where you have to apply some amount of force to create some amount of change in height of the spring, some deflection delta. And this equation, I didn't write no, I did. It's right here, 10.9, will give us a way to calculate the spring constant. Now, I will point out, when they're doing this, this is on page 512 in the 10th edition. Yes. They start out with a energy balance method, so Castigliano's theorem, to get to a spring constant, or to get to a deflection, which will get them to a spring constant. So this is technically an approximation or a simplification of that. So it's another thing where you get close enough doing this, but there is a more exact way if you really had to. But this is an approximation. Now, maybe it doesn't look like an approximation with all these decimal points. Let's get rid of some of those. There we go. Now it looks like an approximation. And so it's just your wire diameter, your modulus of rigidity, which we had to go find from our material that the spring's made of, our mean coil diameter, and the active coils. So you can kind of start to see that there is a progression of things you have to know You know, we have to find the spring index, then Bergstrasser, then the stress. I guess you don't have to calculate the stress, but you do want to make sure that you're not exceeding some shear strength. Active coils, you need the active coils to calculate the spring constant. You need the spring constant to calculate deflection, and so forth. So there are a lot of dependencies here in the spring calculations. So we have this spring constant for our spring says that if you apply 171 pounds to it, remember we're applying 800, but if you apply 171 pounds, it will compress 1 inch. So that seems reasonable for something the size of this thing. I don't know if I pointed out the wire diameter. So the wire diameter is a 1/2 inch diameter on the wire that makes this thing, and the mean coil diameter is 4.5 inches. So these are much larger than the little springs we're looking at over here. So they're much larger. Here we've calculated deflect. This is just Hooke's law. So delta, the amount of deflection. I think your book uses y a lot of times for the deflection, the variable y. Same thing. I just wanted to use delta, I guess. So the force for us is 800 pounds, and the spring rate or spring constant. And this says that, remember, it started out, I don't remember, 12 3/4 inches tall. Yes, 12 3/4 inches tall at its free length. And when it's installed and the car is sitting on the ground, putting all 800 pounds of force onto it, it is going to compress by 4.67 inches. So it's going to get shorter by that amount. Here's a new term. This one, it also comes from this chart. We have the solid height. So, solid length here is what they call it. And here I might have used the, I used the wrong one, because look, we'll have to fix this. We are squared or closed ends, solid length LS. So this is if you compress it, if you're able to, you know, force is not an issue, and you're able to compress the spring all the way solid. So let's see if we can do that. I might have a chance to do it on the little spring. I don't think I can even make this one go solid. But if we can probably make this one go solid. So you compress it all the way down, and all the coils are touching one another. You can't press it anymore without like squishing the wire. So that's the solid height. Now, a lot of springs, this one in particular, if you do that, it's going to try to shoot out of there. That's something we're going to have to look at in a minute, because springs can buckle too, and they might not be stable. So now this spring, it doesn't matter, because normally it is, let's see, you know, it's supported, right? It's on a rod of some kind, and it can't buckle because it's got a rod through the middle of it. Actually goes on this end, but not all springs are supported. Some are inside a hole, some have a rod through the middle to keep them from buckling, and some are designed to just not buckle at all. So first let's go back to MathCAD, and let's fix our solid height, because I put it as the solid height is D times the total number of coils. That is if they were squared and ground. Ours should actually be total number of coils plus 1. So there's our solid height. That might have changed some of our calculations. Hopefully we still have viable numbers at the end down here. All right, so we squish the spring all the way solid, and this would be the height. Now, chances are it's going to take a lot of force to do that. In fact, right here, we're calculating that. So what we're doing here, we're calculating what's called the fractional overrun to closure. So this is basically how much percent squish do you have left under normal operating conditions in your spring. So you're not normally ever, I mean, there might be some case where you want to close the spring totally, get all the coils touching, but that is typically not what you want to do. And so this is going to tell you what percent you have left to be able to squish. So again, page 520 has a guideline on this. Xi should be greater. The Xi is the fractional overrun to closure. That's the percent number. Ours ends up being 77%. So we got a lot of squish left. It should be greater than 15%, 0.15. If you have a spring that's in operation and it only has 15% overrun, then you're probably operating it too close to being closed, and you don't have a lot of room for, hey, the force suddenly is, a larger force than what you designed for. You might end up closing the spring, and that's usually not going to be good. So what we did here is we figured out how much delta, so how much do you have to compress the spring to get it to close. So here's your free length, here's the length it is when it's closed. So this is the 12 3/4, this is the 4 1/2, and you just subtract them. So you have to deflect or squish the spring 8 1/4 inches to get it to close. Okay, knowing that number, and our spring rate, the 171 pounds per inch, then you can figure out, well, it takes 1,400 pounds. Again, there's some approximations in there that K is an approximate, so we're going to make it look more approximate. 1,400 pounds to close our spring. We're applying 800 pounds. So basically this is figuring out what percent we have left. So this equation actually is an equation in your book, I believe. I didn't write the equation number. Let's see. Where is that? It is equation 1017. And it's not actually solving for xi, the fractional overrun to closure, but it's solving for the force at solid. We solved for the force at solid another way, and then backed out the value for xi. And then so this is just solving this equation for xi. This one's not in your book, it's just solving that equation. Okay, so we're good. We have 0.77 and we have to be greater than 0.15. So that looks good. All right, this is okay. Everything looks like it's okay. The spring is in the right range of coils. It's in the right range of fractional overrun. Number of active coils look good. It fits in our design. What about, is it going to buckle? Because we don't want the thing to buckle. So here what we have are a series of equations. These are all on page 514. I think all of these are. There's a whole, well, chapter 10.5 is called stability. These C1 and C2, now in your book they're actually C'1 and C'2. I just don't have a way to put a prime symbol up here that I know of. If anybody knows how to put the prime in MathCAD without it doing things, just being a marker, then let me know, because I'll add it in there. But I guess maybe can't do that. Anyway, it's not important. C1 and C2, these are elastic constants, and as you can see, they're made up of your modulus of elasticity and your modulus of rigidity. So these are constants that are going to go into an equation later on down here. Here, alpha is similar to the end conditions, if you remember anything about column buckling. So remember, we're talking about buckling here. So if you remember about the Euler's equation, things like that, the column had different end conditions. And your book, let's see if we can find the end condition chart. It may not be in the ones I have. Let's see if we can find one. I don't think it's in here in my list of stuff that I have easy to find. What's this one? Let's see. Oh, there it is. All right. So table 10.2 is the variety of end conditions that you might have. So you've got one between flat parallel surfaces and they're fixed. So you put alpha equals 0.5. I actually used alpha equals 1 because that to me is, they're not actually hinged. So we got to go back to our original diagram or original picture. They're not literally hinged. There's not like a hinge up here, but they're also not clamped into this pocket either. So the ends are free to have, oh, you're not being able to see that. That's over here. The ends are, they're not clamped into these control arms, upper and lower control arm. they're just sitting in pockets there, and so they're retained, but they're not really clamped to it. And these surfaces are kind of parallel, so I would not be offended if you put 0.5 in here. But I did use 1 to say that these ends could pivot if they wanted to, sort of like they were hinged, but it's not like they're freely hinged right there. So probably reality, the alpha value we need to use is somewhere between 1 and 0.5. And there is one, you know, there is 0.707, but that's one end is supported and one end is pivoted, hinged. So they're not this. One end clamped, other end free. That's like you've got it clamped at the bottom, and the other end is nothing constraining it. So it's, you know, it's just sitting. Oh, got all my. It's just sitting there like this, on clamped on the bottom, and the top is plenty free to move around. So it's not that. So I chose 1. Both ends are hinged or pivoted, and so it's probably not quite as bad as a 1. But I don't think it's also quite as good as a 0.5 being clamped into the ends. So I chose 1 just to be a little more conservative. So that's alpha. Let's get back down there. So that's alpha, the end conditions, table 10.2. Here, I've got the effective slenderness ratio. So remember there was a slenderness ratio in column buckling also, if you remember that. This is equation 1011. Takes the free length, that end condition, and the mean coil diameter and calculates a number, 2.8. I don't think that is one of the terms that had a, no it doesn't. It doesn't have a guideline for what a good slenderness ratio would be. But then you get equation 1010. So this thing is in your book. I think they actually have a Y here. Yes, they have Y critical because they're using Y as deflection, or you know, how much has it closed. And delta makes more sense to me for that variable instead of Y. So I put a delta here, just what I'm more used to. So the free length, there's those C1 and C2, those elastic constants that you calculated earlier. There's your effective length, which has the end conditions built into it. And you get a amount here. So this is the number of inches that if you were to compress the spring this amount, 6 inches, then it has gone critical and buckled. Remember, we were compressing it, where's our 4.7 inches. So we're close to that, but we're under it. So in our current operating condition, with the 800 pounds on it, it shouldn't actually buckle. I guess you could figure out how much force will it take to buckle it. So you could take this deflection, your spring rate. So force to buckle, or let's do force critical since I use CR on the other. Force critical is delta critical times K. So I want it to be, oh, what a decimal, I mean, there we go. So if we applied a little over 1,000 pounds, then this spring would buckle. We might not want it to buckle since it's part of an automobile suspension. It is constrained, you know, it's not a lot of places it can go. And we probably overestimated. Let's see what happens if we put our 0.5 in. Well, actually, if we put 0.5 in, we get an imaginary number. So that would give us, that tells me that this number is greater than 1, and we're having to take the square root of a negative number. So let's go back to our 1. There we go. There are ways to make it unconditionally stable, so it won't buckle no matter what. Assuming you're applying an axial force. I guess you could apply some moment to it to force it to buckle, but as long as you apply an axial force, then you can make it unconditionally or absolutely stable. I don't remember exactly what word your book uses, but either one of those words mean the same thing for what we're talking about here. They use absolutely stable is what they use. And so this equation, I guess I should put the equation number. This is equation 1012. Okay, and so I put it in MathCAD, and you need to pick one of these variables to solve for. So I'm going to say that I keep the free length the same and change the mean coil diameter. So if you do that, this equation is doing that. So this is solving equation 1012 for mean coil diameter. So it says that for it to be unconditionally stable, we would actually need a mean coil diameter of almost 5 inches. We started with a mean coil diameter of 4.5, so not far from where we're at, but we would have to increase this. Now, if you increase this to 4.99, or it's 5, let's call it 5. If you increase this to 5 inches, then everywhere, like we changed our spring index, which changes our Bergstrasser, which changes our shear stress, doesn't change that. It would change our spring constant, so our spring rate. So it changes pretty much everything about the way the spring acts, particularly the spring constant we might not want to change. So if we switch to this wire diameter, we probably would need to change the wire, this spring, that's right, mean coil diameter. Then we would need to change the wire diameter to keep the same spring constant. So we'd go up here. They're both in this equation. So we would set, let's see if we can do that real quick. I don't know. Control C, let's bring it down here. So this is equal to 171 pound-force per inch. And we want to solve for this guy. We get some imaginary numbers. We don't want those. So the new wire diameter, we need to equal this thing. Don't want it in feet. So we'd have to bump up. We started out with a 1/2 inch, I believe. Let's double check. Yeah, a 1/2 inch wire diameter. We would have to go up to 0.54 inch wire diameter if we increase the coil diameter. And if we did that, now we would have the same spring rate as before. So particularly in an automobile suspension, that's probably important to keep the same spring rate. We have the same free length because we didn't change that. We only changed the mean coil diameter. And now we've changed the wire diameter to maintain the spring rate so that our performance is the way we want it from our original design. Maybe we wanted that, we were counting on that spring rate of 171 pounds per inch that we originally planned on. So there's a lot of different ways and a lot of interactions between springs. They're really interesting like this, where you change one thing and you've got 3 or 4 other variables that you can change to get back to where you were to meet your design constraints. There are other constraints, physical ones, that maybe we can't put a 5 inch coil diameter into this. Maybe we have to keep that coil diameter the same, so maybe we need to change the wire diameter and do something, or change the free length, which changes the height of the thing. So there's a lot of different variables that you have to consider with springs, and that's why I'm doing it in MathCAD, is so that every time I make a change, then it automatically gets filtered through the rest of my equations. Okay, hope that was helpful on springs. We'll do a couple of more discussions on springs, extension springs next. So what happens if you pull on a spring? And then I think we'll do some of your lesser known, like torsion springs, maybe some flat bar springs, stuff like that. But we should be good for now. So I will see you next time.